Chapter 10, Chemical Bonding. Bonding theory. There are two kinds of bonds, the ionic bond and the covalent bond. In the ionic bond, you have a positive charged cation attracted to a negatively charged anion, such as sodium chloride. So sodium gives away its electron, becoming positive ion, and chlorine accepts an electron, becoming a negative ion. And so here we have the positive ion attracting the negative ion, an ionic bond. There's the covalent bond. This is where atoms are held together by sharing a pair of electrons. An example, hydrogen has one electron and the other hydrogen has one electron. They form a pair, a bond pair, and the two atoms are held together by this attraction to the bond pair. There's also a polar covalent bond, which is similar to the covalent, but the electron pair is not shared equally. For example, in water, oxygen attracts electrons more than hydrogen. So here's the shared pair drawn closer to oxygen. And so this is a polar covalent bond. The Lewis bonding theory is named after G.N. Lewis, who's an American chemist, and he developed it. We simply represent electrons as dots, and we draw what are called dot structures or Lewis structures to represent molecules. Lewis theory is a simple method for making quick everyday predictions about molecules. For example, this is the Lewis structure of methane. There's covalent bonds between hydrogen and carbon. Here's a bond pair, another bond pair, another bond pair. So carbon has 4 bonds, one to each hydrogen. How do we represent valence electrons with dots? Oxygen. Its electron configuration is 1s2, 2s2, 2p4, but remember valence is the outer shell, so the second shell is the outer shell, and it contains 6 valence electrons. So the Lewis structure for oxygen is oxygen, 1, 2, 3, 4, 5, 6. 6 dots represent the valence electrons of oxygen. Each dot represents one of the electrons, and it's placed around the element with a maximum of 2 dots on each side, each of the 4 sides. Although the exact location of the dots is not critical, we generally fill the dots in singly first and then pair them up. This is just a convention. It's important to follow this convention when we were doing homework in mastering chemistry. Here are the Lewis structures of the period 2 elements. As you can see, they are filled in with lithium having only 1 electron, boron having 3 electrons, and note each one single. Finally, in nitrogen, we put 1 on each side, and then we have to pair the next one up. So these are the Lewis dot structures of the elements. We can easily see how many valence electrons they have, and know that when you have 8 electrons, this is a happy atom, and it's got filled outer orbit, and it's got 8 dots, called an octet. How do you write the Lewis structure of an element? Well, for instance, for phosphorus, we know it's in group 5A, so it has 5 valence electrons, and so we need 5 dots. We simply put the 5 dots around the phosphorus. That's the Lewis structure for phosphorus. A stable configuration consists of 8 electrons in the outer or valence shell. This is called the octet rule. And in chemical bonding, atoms transfer or share of electrons in order to obtain an outer shell with 8 electrons. The octet rule applies to all main group elements except hydrogen, lithium, and beryllium, and these elements are stable with only 2 electrons, a duet. Lewis structures for ionic compounds represent transfer of electrons. When metals bond with nonmetals, electrons are transferred from the metal to the nonmetal. Metal becomes a cation, nonmetal an anion, negative. The attraction between the cation and anion results in an ionic bond. In Lewis structure, we represent this by moving electron dots from the metal to the nonmetal. For example, potassium chloride is a compound of potassium and a metal and chlorine a nonmetal. We simply show potassium, we show that, and what we show is a transfer of this electron to here to form the negative and positive. So here's how it looks. K positive, and then in brackets, so you show it's the whole charge of the anion is negative. Suppose you're asked to write the Lewis structure for the compound magnesium oxide. Magnesium has 2 electrons, oxygen has 6, and what you see there is that you can put both electrons to one electron here to complete that, and the other electron here, giving a -2 and a +2 charge. So the formula for magnesium oxide is MgO. The Lewis theory predicts the correct compound formulas for ionic compounds. For instance, sodium sulfide, you see sulfur is lacking 2 electrons. It has 6, it needs 2 more. So one sodium provides 1, and the second sodium is required to provide the second one. Therefore, sodium plus, sulfur -2 sodium, and the correct formula is Na2S. Covalent structures are shared electrons. When nonmetals bind together, a molecular compound results. Molecular compounds contain covalent bonds in which the electron is shared between atoms rather than transferred. So in Lewis theory, we represent covalent bonding by allowing neighboring atoms to share some of their valence electrons in order to obtain octets or duets for each atom. Example, hydrogen, oxygen. With these simple Lewis structures, they combine in this way. 6 here, 1 from hydrogen, and 1 from a second hydrogen gives you the 8 that you need for the octet, and the 2 that you need for the duet of hydrogen. The shared electrons are those that appear in the space between the atoms. You notice that those are bond pairs right here, shared. However, there are 2 other pairs called lone pairs, and we'll discuss that a little later. So the important thing is the shared pair are the bond pairs. The ones that are not shared are the lone pairs. So here's a correct dash representation of a bond pair can be represented by a dash. Lewis theory explains why halogens are diatomic molecules. Basically, chlorine needs 1 more electron, and so what happens is that each chlorine they share their lone electron to form a bond pair. It also predicts that hydrogen would be diatomic because they need to share their single electrons to form a bond pair. Let's look at the idea of double bonds. We know that oxygen exists as a diatomic molecule. But if we take 2 oxygen atoms and pair them together and try to write the Lewis structure, we don't have enough electrons to give each oxygen an octet. 6 electrons and 6, so we end up with this has a complete octet of this oxygen has a complete octet, but this one does not. It has only 6. So what happens is we come up short of electrons, and we've already used our 12 electrons that we started out. Then we can take a lone pair and move it in as a bond pair. That way it counts for both. So we'll do this by taking this lone pair here and moving it in between, looking like this. Now There's 8 around this atom, counting this 4 again, and 8 around this line. We now have each atom having an octet, and that is done by having a double bond. So double bonds show that atoms can share more than one pair of electrons to get the octet. You see, this has the octet, and these 4 count for both atoms. Triple bond, the same thing can happen. For instance, nitrogen, each nitrogen has 5, giving you 10, and here we have represented the 10 electrons, but you notice that there's only 6 around each one, so we need to in fact move a pair in from each atom to create a triple bond. Then in this case, then each atom, here's the octet for this nitrogen, here's the octet for this nitrogen, and so we have a triple bond in nitrogen molecule. So when 2 electron pairs are shared between 2 atoms, that's a double bond, and double bonds in general are shorter and stronger than single bonds. And this tells you a little bit about the distance, the shorter and stronger bonds. Double bond is 121 picometers, shorter than 148 picometers of the single bond. Triple bonds are even shorter and stronger than double bonds. So looking at the example of nitrogen, triple bond is 110 picometers. So how do we write Lewis structures and do this correctly? The first thing is to write the correct skeleton structure. The skeleton structure shows the relative positions of atoms, but it doesn't include the electrons. For instance, oxygen is generally a central atom, and the ones placed here as a center on the outside are the peripheral atoms. In many cases, hydrogen and oxygen are peripheral atoms. So in order to write the correct structural formulas, you have to remember 2 guidelines. First of all, hydrogen will always be terminal or peripheral because it only requires a duet. It'll never be a central atom because one bond it can form and that's it. Secondly, many molecules tend to be symmetrical. So when a molecule contains several atoms of the same type, these tend to be in the terminal or peripheral positions. There are some exceptions. But let's try our hand at writing some Lewis structures. The first thing we do then is write the skeleton, calculate the total number of electrons to be used by summing the valence electrons from each atom. And the number of valence electron is the main group element according to its group number in the periodic table. Remember, if you're writing a Lewis structure for a polyatomic ion, the charge of the ion must be considered when calculating total electron. If it's negative, you've got to add 1 electron. If it's positive, you have to take away an electron. So distribute the electrons among the atoms, giving octets or duets to as many atoms as possible. And you do this in a particular way. First of all, you bond the thing, you put 2 electrons to form a bond pair between each pair of atoms. Then you subtract these electrons that you've used up to form bond pairs, and then you distribute the remaining electrons to the peripheral atoms first. That is, complete the octets. Then you check. If any of the atoms lack an octet, then you're going to have to move lone pairs on the peripheral atoms in to form double bonds or triple bonds. That way it'll count for both. So we say write the Lewis structure for carbon dioxide. Well, first of all, we're going to put the carbon as the central atom and the oxygen as the peripheral atoms. That's the skeleton. The second, we get the total of electrons. We know that each carbon in group 4 brings 4 electrons, and each oxygen in group 6 brings 6. And we have 2 oxygens. So we got 2 times 6 is 12 plus 4. We got 16 electrons to work with. Then what we do is we put in the bond pairs. And you notice we made 2 bonds, which is 4 electrons. So 4 of the 16 are used in forming the bond pairs. Sometimes you show the bond pairs as a line. Now we have 12 left. So the next job is to go to the peripheral atoms and put, they need 6 more to complete the octet, so put 6 on that one and 6 on that one. Now we have the 12 plus 4, we have the 16 electrons used up. We can't add any more. But then we notice something. The octet of the central atom is not complete. It only has 4 around it. So now we're stuck with moving lone pairs from the oxygen atoms to form in regions to form double bonds. We move a bond pair in here so that it still keeps it and gets counted, and we move a bond pair in here, so we end up with this structure in which all the octets are completed. Check this: 8 around this one, 8 around carbon, and 8 around oxygen. A very happy molecule with double bonds. When you write the Lewis structure for polyatomic ions, you have to write the structure by the same procedure, but pay attention that of the charge of the ion. Let's practice writing the Lewis structure of the cyanide anion. We begin by writing the skeleton structure. It's simply carbon and nitrogen. Then we calculate the total electrons, knowing that each carbon brings 4 electrons and the nitrogen brings 5 electrons, 4 plus 5, and then seeing the negative charge, adding 1 more to give us 10 electrons. So bonding electrons first. We simply connect carbon and nitrogen with a bond pair. So 2 electrons used. We now have 8 remaining. We distribute the remaining electrons as lone pairs on the peripheral atoms. In a certain sense, we have 4 on this one, and we put 4 on this one, and then we have used all 10 electrons. Now, since neither atom has an octet, we're forced then to move some of the lone pairs in. We move one lone pair in from here and another lone pair in from here to produce a triple bond. Now in this situation, nitrogen has a complete octet and carbon has a complete octet, and the cyanide ion then has a triple bond. So in summary, it is important that we kind of follow a process, and it's easy. You write the skeleton, that's just the symbols only. You get the total valence electrons that brought by each atom, and then if there is a negative charge, you add 1 more electron. If there's a positive charge, take 1 of those away. We connect the skeletons with bond pairs. You can show this with a dash if you want. It contains 2 electrons. Then subtract from the total electrons available those electrons used in bonding. Then use the remaining electrons on the peripheral atoms to complete their octets. Now check the octet of the central atom. If it's short, move lone pairs from the peripheral atoms to form a bond pair with the central atom. It's easy, and there's lots of examples. Practice.